Hello, fellow student doctors. This is student B, and today we'll be talking about lecture 4. We'll be talking about equilibrium, torque, and energy. More specifically, I've just broke it down here, our agenda for today. We'll be talking about equilibrium. We'll be talking about static and dynamic equilibrium. Talking a little bit about torque, and we will be also, 1 second, talking about a car engine application. And that car engine application, we're going to use that to understand torque, energy, and systems. All right. So this application is going to go from bullet point 2, 3, and 4. After we finish torque, we're going to talk about, while we're talking about torque, we'll talk about rotational motion. And then we'll get into energy, units of energy, types of energy, right? Mechanical energy. We're going to talk about the conservation of mechanical energy. And we're going to talk about non-mechanical energy, so chemical energy, stored energy in atomic in atoms. All right? And we'll also be talking about systems, right? Closed system, adiabatic system, open system. And we'll also end that with kind of an application to the universe and how that relates to the idea that energy is not created or destroyed. And we'll end today's session by talking about work, all right? And how energy is transferred within these adiabatic systems and closed systems in the form of heat, or friction. All right, so let's talk about equilibrium, right? So when we think about equilibrium, we think of a steady state of no change, right? Maybe a going of back and forth between two different states, but overall a settling at a finite point, right? So let me just draw two different examples. So let's draw our free body diagram, right? We have our downward force. So force is equal to mass times gravity, right? That's our gravitational force, right? And then we also have our normal force, right? This is the normal force is the force that the Earth is acting back up on that object, right? So that's the normal force. All right? When we talk about the idea of equilibrium is defined as a state where there is no translational acceleration, okay? No translational acceleration. All right. So when we talk about translational acceleration, what are we talking about? We're talking about the movement of an object across the plane, like as if you were going to slide this block over here, right? And you were using a force to do that. That would be an example of translational acceleration, right? But in equilibrium, there is no force that is applying that force so that acceleration is occurring, right? So in a state of equilibrium, there is no translational acceleration. Right? And in other words, velocity is constant. Okay? Velocity is constant. Right? If the object is moving in this direction, right? And there's a force being applied to it, then velocity, V initial, is not going to be the same as V1, V2, V3, right? Because there is acceleration taking place here, right? So this system, if there was a force applied, would not be in equilibrium. But you could still have an object sliding, right, if the velocity is constant. So if the velocity at this point was v1, right, and the velocity at this point, right, of this moving object was v1, so v1 was equal to v1, right, and this object was the same as the acceleration here, right, at this point. So you're going to have right, three different velocities that are constant, right? In that case, we would still be in a state of equilibrium because why? There is no force acting on the object. Although there's a constant velocity, there is no actual force acting on that object. So that is one case of translational or one case of equilibrium, right? So we're going to talk about these two different types of equilibrium. One state is a steady state where the object is not in motion, so not in motion. And one where an object is in motion. And that is going to be the difference between static and dynamic equilibrium. All right? So let's look at our next example. So let's look at another example here. So we have this idea called static equilibrium. So static equilibrium looks something like this. So we have a plane object. Force of gravity is equal to mass times gravity, right? And we have a normal force, right? And so we have a system where, the both forces cancel out, right? So Fg is equal to force of normal. And because of that, you have an object not in motion on the vertical axis. All right. So there's no velocity. There's no so the velocity of this system is 0, right? Because there's no force acting on the horizontal axis this way or this way, right? This object is just sitting on a table or something like that. So this velocity is 0. Both forces cancel out, right? So force of N is equal to force of gravity. And because of that, this is considered static equilibrium. Static equilibrium. All right, and now I'm going to show another example, and this is going to be dynamic equilibrium. All right. So let's look at dynamic equilibrium. All right. So let's say we have this guy that is about to jump off this plane, right? All right. And here's this guy sideways, and he has his parachute, right? As he's jumping off this plane, right? What's happening here? So if we take this look at this guy, and we create a free body diagram, right? This free body diagram of this guy is going to look like this. So he's going to have the force of gravity acting on him downwards, right? And he's going to have a frictional force, right, acting or opposing him. This frictional force is what we call air resistance. All right? And as this guy progresses, he's going to keep going down, 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 down. And he's going to get to a point, right? Use this guy. I'm going to draw him again. And he's going to get to a point where both of these forces, the air resistance force and the force of gravity, are equal to each other, right? And this point here is called terminal velocity. All right? And this is the point where the force of gravity is equal to the frictional force. At that point, or the force of air resistance, right? And the way I kind of imagine air resistance is, if this guy was, falling, his body, all the atoms in his body are interacting with the sea of air molecules that he's coming in contact with, right? And it's causing a counter force against this force of gravity that's acting this way, right? And he's going to get to a point where he's going to encounter so many air molecules, right? So many air molecules that the downward force that he is experiencing is equal to the resistance force that he's experiencing. And that's what we call terminal velocity. And that's how I picture this step right here. All right? So the idea is dynamic equilibrium is when, all the forces acting on a free body diagram is equal, but somehow the object that the forces are acting on are going through or experiencing a constant velocity. So an object that is experiencing dynamic equilibrium, right, will be going through constant velocity. And in this case, that is called terminal velocity. So to sum up equilibrium, an object can be in static equilibrium or dynamic equilibrium. A static equilibrium object has a velocity of 0, so the object is not moving. But in dynamic equilibrium, this object is experiencing both a constant velocity, but while all forces acting on the object, right? All forces acting on the object are in a state of equilibrium, right? So like the parachuter, right, or the free faller, he's going to be in a state of terminal velocity at some point as he meets his match with all these air molecules that are resisting his downward force, the force of gravity, right? We can also say, right, because of that, we can also say this man, the force of gravity that he's experiencing minus the force of air resistance is equal to 0, right? And because of that, right, since force is equal to mass times acceleration, this guy is experiencing zero acceleration. Zero acceleration, all right? Zero acceleration, right? But he is experiencing a terminal velocity. All right, so zero acceleration, terminal velocity. If we look at this example, right, this guy is having zero acceleration, zero velocity. All right, so this next thing we're going to talk about are systems not in equilibrium. All right, so now that we've looked at systems in equilibrium, right, let's kind of look at some systems not in equilibrium, right? So an object that is not in equilibrium will be either accelerating transitionally or rotationally, right? So if we had this object, right, either there was a force acting on this guy and he was moving in this direction, right? And there was this force, right? That would be transitional acceleration, right? Or if we dropped an object from the sky, right? And initially before he hit terminal velocity would have a downward force, right? And it would be much greater than the air resistance, right? So there would be a net force downward. And then we're going to talk about rotational acceleration or angular acceleration, which can be understood when we study about torque, right? Torque is the conversion of an applied force into rotational motion. So we'll be talking about all of these different systems, accelerating transitionally and a torque as well. Okay, so let's go ahead and look at this example. Let's look at an example here. We have a system, okay? All right. Let's just say this object has 10 kg and it's being dropped, I don't know, from a cliff, okay? So, force is equal to mass times gravity, so 10 kg times 10. Right? So that's the force. So this guy is experiencing a force of 100 newtons, right? 100 newtons downwards, and he's experiencing some air resistance, right? But it's negligible, right? Because we're dropping it from a cliff. All right. So would this object be in equilibrium? No, right? It wouldn't be in equilibrium, right? Because the net force is downward. And because of that, right, we have an acceleration, don't we? All right. So this is an example where a system is not in equilibrium, okay? So the initial part of a free fall. Okay. And how about this example? Let's just say we have this car, and it's accelerating from 0 to 20 miles per hour, right? Since there is an acceleration, right, from V initial to V final, right? This object will not be in equilibrium either, right? Because there is an acceleration from 0 to 20 miles per hour, and because of that, there's a net force acting on the object in this direction, right? There is kinetic friction, right? There is the force of kinetic friction acting on the tires, but that is negligible also, right? So in this instance, this system will also not be in equilibrium. All right? All right, so the next topic that I want to discuss is torque. So torque is a twisting force. All right, so torque is a twisting force, right? So the actual equation for the magnitude of torque is equal to the radius times the force applied to the side of the axis that it's spinning on, right? Times the sine of the theta between the two variables r and f. And because of that, since there are two vectors involved, we are actually 1 second. I'll erase this. Because we are multiplying by a vector, we can understand that torque is also a vector, right? All right, so usually for the MCAT, all we need to know is that torque is directional, right? So it can either spin clockwise, the twisting force is either clockwise or counterclockwise. All right, and so let's just see an example of torque. Okay, so let's just say we have this seesaw. Okay, all right. Right, and we have an object right here, and it's applying a downward force of mass times gravity, right? Because there's a gravitational force acting downwards on it, right? And if we set this as the axis of rotation, right? Because this would be the fulcrum of the seesaw, right? We could also say that we have a radius here. Right, and let's just say we're going to say that the direction is this way, right? We would, if we use the right hand rule, right, which I'll explain how to figure out or show you how to get the direction of the torque, right? Because torque is a vector. What we do is we would take our right hand and we would use our fingers and point it towards the direction of the radius, right? And we would point downwards because the force is pointing downwards, and we will rotate our hands around to make a grip, and we'll realize, and we'll stick our thumb out, and we'll realize that the thumb is going out of the page. Okay, so and how do we denote out of the page? All right, so out of the page is denoted as a dot, a pencil dot and a circle. Okay, and the way to think about this is if you were to look at a pencil, right? Say this is a pencil, this is the tip, right? And here's the pencil, right? If you were looking at the pencil and you were pointing it towards you, and you were looking at it as if it was coming towards your eyes, you would probably see something like this. All right, and so we would call that out of the page. Right. Now, if you know we were pointing this pencil, right, and let's just imagine that we have this sheet of paper, right? So now let's imagine we have a sheet of paper, okay, and all of a sudden you decide that you want to go into the page, right? If you go into the page, you're going to cause a crease here, right? And that crease is going to look like an X, because you'll be puncturing the paper, and so it'll look like that. We call that into the page. Into the page. All right? So the direction of this torque is into or out of the page, right? Now we know the direction of the force of the torque. We know that it could either be into the page or out of the page. So then you might ask, how did we get the idea of clockwise and counterclockwise, right? And we'll get to that. But first, what I want to show you is how torque is, right? Torque is a rotational force, right, that can go either clockwise or counterclockwise, right? But since we're looking at it from two-dimensional, right, we're just drawing this on a sheet of paper. This is two-dimensional. If we looked at it three-dimensionally, the torque would actually be coming out of the page, right? So that means that if you looked from the top, if you applied this force and you had got rid of this fulcrum, the actual torque, right? The actual torque would look something like this. All right. Now, if you imagine a clock, right? So let's just say you have a clock. 12, 2, 6, I don't know, maybe 8, okay? 8. And you spin it this way, that would actually be counterclockwise, right? So this would be considered a counterclockwise torque. All right? And likewise, if we had a direction that was into the page, right? All right, 12, 2, 6, and 8, right? And that torque was going out of the page, right? So if we looked at it from a two-dimensional perspective, right, and we had said that the pencil was going into the page, and we looked at it from the side, and we saw that the direction of the torque was into the page. If you imagine the pencil pushing through that page, it would go something like this, right? And if it went something like that, let's look at a clock. It would be going what? Okay, my bad. 1 second. All right, so we had a small issue there. So let's erase this, right? Let's just say we were going into the page, right? And the problem that we had here was that we didn't base it based off of our radius and our force, right? But if we were going into the page, and I'm guessing the force, we would have to do the right hand rule, right? So now you notice the problem, right? If you do not use the right hand rule, you can make the mistake of misunderstanding counterclockwise and clockwise rotation, right? So here we assume that it was we made the mistake of saying that it was counterclockwise, but in actuality it was clockwise. All right, so clockwise. So let's look at another problem, right? And maybe we can better understand the difference between counterclockwise and clockwise torque. All right. All right. So let me go ahead and fill this in right here. And counterclockwise. Okay. Counterclockwise. So we made it. We actually, I think this. Let me just go ahead and do this whole example again on a different sheet of paper. Okay. So let's just say we have this example, right? We have our seesaw, right? And we have an object that is at a fulcrum, right? And there is a radius here, right? And there's a downward force by gravity, right? Remember, torque is a vector, so it's RF sine theta, right? Force is also a vector. On this other side, we have, I don't know, another object, right? And it is doing the same thing. Has a force of gravity. So we have two torques in place here, right? We have all the components for torque, right? R, we have a radius, distance from the fulcrum. We have downward force. On top of that, we have our sine theta, right? So let's look at our sine theta, right? All right. So we have our sine as well, right? We have our sine of theta, which is 90 degrees here, right? Degree is 90 degrees. And the sine of 90 degrees is 1. So we have a torque that's equal to R times F, right? Force is that way. So if we use our right hand rule, let me explain right hand rule. So let's say this is your right hand. I'm going to try to draw the right hand, okay? So we have our right hand, right? So this one is your right hand, right? You have to put your right hand right in front of you, right? And then what we're going to do is we're going to use our fingers. Okay, so we're going to use our fingers, and we're going to, so this is step 1, take your right hand. Step 2, we're going to take it and point it towards the radius, pointing towards the box. Pointing towards the box. So we take our right hand, and let's just use this example on the left side first, right? We're going to take our right hand and we're going to point our radius, or we're going to point our fingers towards the radius, towards the box. So I'm trying to do the right hand rule right now, and I'm pointing my fingertips towards the box. So now looking at it, my fingers are pointing west, right? Never eat soggy waffles is pointing west, right? And then what we're going to do is we're going to take these fingertips. So let me just go ahead and draw this, right? So this is how your fingers are going to be looking, right? This is your hand. Let's just say this is your hand. And so now you're pointing this way, right? So you're pointing your hands towards the radius. And the third thing that we're going to do, right, is we're going to curl our fingers in the direction of the force. So now we notice that the force is going downwards, right? So now we're going to take our fingers. So let me go ahead and change colors one more time. Okay, so we're going to take our outward or westward pointing fingers, right? Never eat soggy waffles. Westward pointing fingers, and we're going to curl them, okay? Let's curl them down, okay? We're going to curl them down into this fist. So now we have this fist, all right? And this is our fist. Okay, and, let's just say, we're making a punching hand, okay? And now the only thing we have left to do to know the direction of the torque is to stick our thumb outward. All right? And then our hand looks something like this. Right? So when our hand is pointing outwards, you'll notice that our thumb is pointing towards us, right? So if we were the page, right? So let's just say we were the page, okay? So let's just say we were the page. So let's just say I'm looking at myself and I'm pointing the thumb towards me, right? So I'm pointing the thumb towards me. Okay, so this is the thumb. Okay, let me just erase that. And I'm pointing my thumb towards me, right? Let's just say this is me, and I'm looking at myself, and this is me, right? And my thumb is pointing at myself, right? Because I made it into a fist. I used my pointer finger, my whole 4 fingers, and I pointed it towards the direction of the radius. I curled my fingers towards the force, and I stuck out my thumb, which is the direction of our torque, right? So we decided that we were pointing outward. And so we're pointing this finger towards us, and we said that we need to make sure that we're imagining ourselves as the paper. So if we were the paper, right, then this pencil or this finger, all right, will go into the page. Right? So you have a pencil, right? We have our pencil, and we're pointing it towards the paper, right? So if we puncture the paper, right, and it comes through the other side, right, what's going to result is a puncture, right? A puncture. And that puncture is what we're going to be calling into the page. Okay? So this would be into the page, right? So R, F, and the thumb is pointing outwards, so torque is this way, right? And remember we talked about the clock. So now we have a directional component. So we looked at it because torque is a 3-dimensional force, right? Or is in 3D, right? It's not in 2D. So you have to think about it in 3D. So 12. Okay. And so if we're going into the page, right? Into the page. Okay, hold up. Into the page. So R, F is pointing into the page, Or no, sorry about that. It's going out to the page. It's going out of the page. It's going out of the page. I don't know what I was thinking. Out of the page. Out of the page, right? And we went from here outwards like this, right? Because we're going out of the page. What we would see is counterclockwise direction, right? So this torque would be out of the page, all right, out of the page and counterclockwise. All right, so now let's go ahead and look at this. So we said this was. So now let's look at it from the other hand. So we're going to use our right hand rule. We're going to do the same thing. We're going to go, we're going to use our right hand, point our fingers towards the box, right? The radius going outwards, force is going out, right? And this force would be going into the page, right? And if you think about it, going into the page, this will be also counterclockwise, right? So we have, when we look at this, right, we have two different forces. We have one force from object 1 going this way, right? And it is going out of the page. We have another object going in this direction, right? And this object is going also counterclockwise, right? This is object 2, and this one is going out of the page, right? Or is going into the page. One's going out of the page and one's going into the page. Overall, the reason why this object or these two masses are in equilibrium, right? Both of these objects are in equilibrium is because these torques, right, actually cancel each other out on both sides. So torque 1 is equal to torque 2. All right, and because of that, this both objects on both sides are in equilibrium. So in that way, right? So in that way, we can determine the torque, right? Because we have to use the right hand rule, and it's a three-dimensional force, right? That if the object is not swinging in one direction, means they are in equilibrium, right? And the torques are equal to each other. We need to consider one more idea, all right? And that idea is that what? When the radius and the force are together and they make a 90-degree angle, this radius right here is called it's called the lever arm. All right, so if ever you have the radius, right, and you have the downward force, and they create a 90-degree angle like they do here, this radius right here is called the lever arm. This is not the same if the radius was going this way and there was a force going this way, because this angle here would be less than 90 degrees. So this radius is not a lever arm. So that's just a terminology that you need to understand when we're talking about torque. All right. So the next thing we're going to talk about is let's do a problem. Okay, so let's do a torque problem. So let's switch back to the black color. Torque problem. All right, so let's look at this example. So we have a pole, right? And let's just say it's a telephone pole, and it has a line, right? A pole, and it has two cable lines. All right. Okay, one is 4 meters. Let's erase that. Let's say it's about 5 meters. One is 5 meters. 5 meters off the ground. And we have a line B. So we have another line. So let's just say this is line B. This was let's just say this is line A, right? So line A is 5 meters off the ground, and line B is, let's just say it's about 2 meters off the ground. Okay. The tensions in line A and B line A and line B are 200 newtons and 500 newtons respectively, okay? All right, and they're asking, what is the net torque on the pole? So let's just go ahead and change colors. Change it right here. So we have this pole, right? All right, and line A is 5 meters off the ground. So let's just say it's right here, and it is 5 meters off the ground. And let's just say this guy is, so let's say line A is 5 meters off the ground, line B is 2 meters off the ground. Okay, so let me just go ahead and erase this. Five meters off the ground. And line B is 2 meters off the ground. Okay, so let's just say this is line B and it's 2 meters off the ground, right? The tensions in line A, right? So this is like a telephone pole, right? So we're going to go here, and let's just say there's another telephone pole here, all right? So we're just drawing this guy right here. And we have another telephone pole over here. And so these are our telephone poles, right? And there's tensions on each one of these poles, right? Or each one of these lines. The tension in line A and line B, okay? So line A is 5 meters off the ground. Line B is 2 meters off the ground. The tensions in line A and line B are 200 newtons. Okay, so this one right here is 200 newtons, right? And this bottom one right here is 500 newtons, okay? 500 newtons, okay? And they want us to figure out what the net torque is, right? So what is the net torque is the question that they're asking. Well, first, let's go ahead and understand how our vectors are looking, right? So what is our radius? Okay, so if I, let me just go ahead and redraw this. I'm going to redraw this. All right, I'm going to redraw this picture on the next page. So let's go ahead and redraw this picture on the next page. So let's draw our three telephone posts. Right? And we have one that's 2 meters off the ground, right? So this is 2 meters. 2 meters. And this one has 500 newtons. And then we have another one that is 5 meters off the ground, right? Then we have one that is 5 meters. And this is 200 newtons, right? 200 newtons. 200 newtons, right? So, let's see. Did we get all that right? Yes, we did. So now let's go ahead and change the color. So we're going to change it to black. And so we have a couple of things that we need to consider. We have our radius 1 here. We have our radius 2 here, right? We have force 1 here and force 2 here, right? And these are both lever arms, right? Or not this. 1 second. These are both lever arms, right? This and this. Because why, right? Because they're creating 90 degrees here. 90 degrees, 90 degrees, right? So they're both lever arms. And now what we need to find out is the directionality of the torque, okay? So we have a radius going up and we have a force going outward, right? Right? And so they're asking us if we use a right hand rule, so radius pointing with our right hand, the fingers, we're curling the force sideways, so our thumb is pointing towards us, right? So let's go ahead and draw that, right? So we have one force going this way, right? And now let's look at this other force. We have a force going upwards, 5 meters, and that's a radius, and we have a force going outwards, right? So let's do the same thing, right hand rule, right, and then the force is going outwards, so you might have to curl a little bit. Then we're pointing that way, so this would be going in the opposite direction, right? Since both of these are going in the opposite direction, right, they're opposites, right? So let's go ahead and set those equal to each other. So torque 1 is equal to RF sine theta. Torque 2 is equal to RF sine theta. So torque 1 is going to be 2 meters, 500 newtons. 500 newtons times 2 meters, right? And the second force, right, is going to be 200 newtons and 5 meters. 200 newtons and 5 meters. All right? And because of that, what's happening here? We have 1,000 Newton meter equal to 1,000 Newton meter, okay? Which means that both torques, right? Both torques on both sides are equal. So here is 1,000 Newton meters in one direction, and here is 1,000 Newton meters in the opposite direction, right? But they're equal, right? And that is why this pole is stable. And that's why these wires are stable here, because the torque is stable here. So the torque on both sides, the net torque, is equal to 0, right? So this system right here is in static equilibrium. Right? It's in static equilibrium because all the forces cancel. The torque cancels, right? and because of that, there's no net force that's acting on this center pole. All right, so let's look at this. The net torque on the pole, right? So the question says, what is the net torque on the pole? Oh, 1 second. So the net torque on the pole, right, would be 0. All right, so now let's look at another question. All right, so that was a good example of a torque question that you might see on your MCAT. And the next thing I want to talk about is the application. So let me change colors again. The application of torque in a car engine. All right. So now let's look at this. Let's look at a car engine, right? So what is a car engine? So if we were to look at this car engine, right, we have a few things to look at, right? So we have the tank, right? And in this tank, right, and we're going to talk about closed systems later, but I'm just introducing you to the idea of the car engine, right? So you have so let me first just draw what I see when I think about a piston and a car engine, right? So we have this, and we have, what do you call, this downward force, and that downward force is going to create a downward force over here, and that is going to translate to the downward force on the wheel, right? So technically what is happening here, right? We're having molecules of the gas, right? The gas that we put in our car, right? It comes through this pipe right here, right? And it enters through here, right? And there's usually a spark plug, okay? So there's usually a spark plug here, right? And this is a spark plug, and this spark plug is going to light, right? It's going to go ahead and add energy to a bunch of these molecules, right? A bunch of these molecules, and because of that, right, that energy has to go somewhere, right? And the way, so we're going to talk about this, but the way energy is utilized is only through two ways, right? Friction and work, right? So friction and work, right? Now, when we talk about friction, we might lose some of this energy in the form of what we call heat. All right, and that heat is going to be what makes, right? It's going to be what makes the outside of this container hot, right? But the rest of the energy will go out in the form of work, right? And work is actually a force applied over a distance. Okay, so what's going to happen here? These molecules, right, have a lot of energy. They even have more energy than they had when they came in, because this spark plug increased the amount of energy within the system, right? And because of that, to maintain equilibrium, these molecules will get excited, right? And they'll start moving more with more velocity, and they'll be dancing all around here, and they will need to release that energy. And so when there's enough energy in this system, that velocity is going to create a force that's actually going to push this system, this lever-like system down, which is considered the piston, right? We're going to push the piston down, and this object is going to go from position 1 to position 2, right? Position 2, right? So now if we look at this, right, we have created, right, a downward force applied to the axle, right? And the axle has a radius, and it's going to create rotational motion of the wheel. And that rotational motion of the wheel is going to be what causes this car, right? So let's just draw this Ford pickup truck here. Let's draw this Ford pickup truck. Our Ford pickup truck. To move forward, right? So the torque that's created from this this lever arm, right? That is created from this downward force by the motion, or by the energy created or inputted by the spark plug, right? Because energy is never destroyed, right? And energy is always conserved, has to go somewhere. So it pushes down on this piston, which creates a downward force, right? That downward force is applied. That downward force is applied to an axle, and that axle causes our wheels of our car to spin, and that is how torque applies to a car engine. Isn't that interesting? And so now that will be a great segue into our next topic, which is energy, right? So how did these molecules, right? How did these molecules use the energy that it had, or how did it gain energy? How did it utilize the energy to create this work on this piston to create this torque? And so our next topic is about energy. All right, so let's go ahead and write. Our next topic is about energy. All right, and so let's kind of define energy, and we will come back to our car engine application more often. Okay, so first of all, energy is measured in an SI unit called joules, measured in an SI unit called joules. Okay? Joules. Okay? And this joules, all right, so joules is also is equal to work, okay? And work is measured in Newton meters, okay? So Newton meters and joules are similar, all right? So here we have, in this car application, we had exerted a lot. We had increased the amount of energy, and that energy was released in the form of work by pushing down this piston, right? Or this lever. And because of that, we can also say that work, right? Work is a form of energy. So say work is kinetic energy final minus kinetic energy initial. So work is also measured in joules. So joules is also, work is also kind of a measure of energy. Okay? And if you think about it, the output of torque is equal to RF sine theta. Remember I talked about the importance of units? The importance of units, right? So if we have a radius, probably it should, if we're using SI units for everything, right? So it would be measured in meters, forces in newtons. Will also give you Newton meters, right? So torque would be also measured in joules, right? So torque, work, and joules, right? Energy are all measured in the same units. So if we were to define torque in terms of energy, what we could say is torque is of work over energy required for rotational motion. Rotational motion. All right. So now that I showed you quantitatively how to think about energy, right? Now I'm going to show you how energy is usually categorized, okay? So energy is categorized into macro and micro, okay? Macro systems and micro systems. Macro systems, right, is what we will define as mechanical systems or mechanical energy. Microsystems will be things like chemical energy. Chemical energy. All right. So when we think about mechanical energy, all right, we think about motion energy, okay? Okay, and this could be anything like an object rolling down a cliff, right? That's mechanical energy, right? A car that is stationary, automatically accelerating and moving, right? That would be mechanical energy. Macro system, right? The movement of large things, rocks, cars, to an asteroid coming towards planet Earth, right? An energy in microsystems, right? Chemical energy would be anything on the atomic level, right? Atomic level. So this could be, right? We can talk about electrical potential energy and circuits, right? Right, we have our battery here, right? And we have our resistor and resistor 2, right? And what's happening here, right? What's happening here is we are talking about the traveling of electrons, right? We're talking about the movement of an electron through a circuit, right? 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 And that would be an example of chemical energy, micro system, right? We can also talk about energy energy that is also created, or energy that's also set in motion when we were talking about, right? We were talking about those fuels, like those molecules in there, like the gas molecules, right? Gas molecules within the chamber, right? When we put the spark plug, right? We added energy, right? We added energy in joules, and because of that, right? We increased the motion, the energy of these particles that were in the system, right? So that would be also another example of a microsystem, a form of chemical energy, right? We also have the idea that let's just look at this, right? So what happened here, right? We converted chemical energy into mechanical energy, and that, right, with our torque, the movement of this lever, or this piston that caused the rotation to create mechanical energy, right? So we used chemical energy, and we transferred that energy from one form to another, to help us go from point A to point B, right? All right. So the first thing we're going to talk about is mechanical energy, right? So mechanical energy, we're going to be talking about the macro side of energy, right? So mechanical energy, right? So mechanical energy, ME, is equal to potential energy plus kinetic energy, okay? And that is going to be true based off of the conservation of mechanical energy, right? So let's look at the law of conservation of energy. So 1 second. All right. And while we're looking at this, right, we're going to break this conservation of mechanical energy. And what this is saying, right, and what the conservation of mechanical energy is saying, is that in a system, a closed system, there is no loss of energy. No loss of energy, but within the system. So whatever energy the system has, it will maintain that energy at any given position within that system. Okay. So it's going to have the total mechanical energy. The total mechanical energy is always going to be the same, no matter what the different stages the molecules, or not the molecules, but the car is at, right? So if the car is stationary, it's going to have nothing but potential energy. But if it's in motion, right, it's gonna have kinetic energy, some kinetic energy, right? So we're always going to maintain our mechanical energy, right? But it's going to be dependent on either one of completely 100% one, or 100% of the other, or it's going to be some ratio of both of these two energy sources. All right. All right, so now let's talk about our first component and let's see the different forms of potential energy there are, okay? So this will be our first topic. We're going to be talking about potential energy and then we'll get to kinetic energy, okay? So let's go ahead and switch over here. Let me go ahead and change this. Let's look at potential energy, right? Potential energy, right? And this is one of the components of mechanical energy, right? Total mechanical energy is PE plus kinetic energy, right? We're going to talk about this component right here. So let's go over here and let's go ahead and look at this. Potential energy can be divided into three sections: gravitational potential energy, elastic potential energy, and elastic potential energy, right? There's also a third form of potential energy called electrical potential energy, right? But we're not going to talk about electrical potential energy here, okay? We're just going to be talking about gravitational and elastic potential energy. All right, so let's go ahead and talk about gravitational potential energy first, all right? So gravitational potential energy. A gravitational potential energy. All right, so let's talk about gravitational potential energy, right? And we're going to denote it UG, okay? So let's go back to the idea of mechanical energy, right? Mechanical energy is kinetic energy plus potential energy, right? And this type of energy based off the conservation of mechanical energy, right? It's the energy is conserved, right? So total mechanical energy will never change. So with that idea, let's think about gravitational potential energy, right? Gravitational potential energy. I'm just gonna go ahead and draw a boulder on top of a hill. All right, and let's just say it is sitting at H max, okay? All right, at a maximum height. And this is the maximum height that it's sitting at, right? Gravitational potential energy, right? UG is actually measured as the mass of this object, right? This object right here, times the gravitational potential energy, times the height that it's sitting from the bottom, right, to the planet Earth, the bottom. This right here is what makes up that H component, okay? This height from the ground, all right? Now, as you transition from here to about here, as you transition from here to here, the mechanical energy done here is going to be solely the gravitational potential energy, right? And you might ask, why is that? Because kinetic energy, okay, so let's define what kinetic energy is, right? Kinetic energy, right? Kinetic energy, by definition, is, all right? So kinetic energy is described as energy energy which a body possesses by being in motion. So this object at the top of this cliff is not in motion. And because of that, we know that the kinetic energy is equal to 0, right? So the mechanical energy is solely based off of the gravitational potential energy, which is the mass times the gravity times the height, okay? Now, if I was here, right, and I decided to push this rock and maybe just gave it a small little nudge, right? Not too much, all right, but just so that gravity could work and it would start falling off, right? And at this point, this object is in motion, right? So at this point, there is kinetic energy, right? There is also still potential energy, right? And why is there potential energy, right? There's potential energy because although it's not at the highest height, it is still a distance h2 from the bottom, right? From the ground. So because of that, we're going to have both kinetic energy and potential energy at this point. So when we're describing, right, this boulder, we can describe it in terms of mechanical energy and gravitational potential energy and kinetic energy, right? And let's just say next the ball comes over here, right? So now we are closer to the ground, and because of that, let's just say height is 0, okay? At this point, our mechanical energy is solely our kinetic energy. So we can see the transfer, how the mechanical energy, right? The mechanical energy, let me go ahead and change colors. The mechanical energy at point 1, so ME1, is equal to mechanical energy at ME2, and is also equal to mechanical energy at ME3. So let me rewrite that. So ME1 is equal to ME2, which is equal to ME3. All right. So let's look at the different types of gravitational potential energy, right? So we know that gravitational potential energy at least from a short distance, right, as long as it's within the atmosphere of Earth's surface, right, so is based off of the mass of the object, the gravity, right, times the height that it is from the bottom, from the surface of the Earth, okay? And that is how you're going to find gravitational potential energy. Gravitational potential energy will always exist if it is at some distance from Earth's surface. Right? Now, let's just say, so what would be the example, right? What would be the example, or what would happen if we took an object? So let's just say this is planet Earth. So let's draw planet Earth. So this is planet Earth. And we were talking about, I don't know, maybe let's just say we have a meteor here, okay? Right? This meteor still has a potential energy from planet Earth. So here's Earth and here's the meteor. So Earth and the meteor. Okay. The way that this is described is through this equation, right? Let me go ahead and switch right here. Gravitational potential energy is equal to negative G times mass 1 times mass 2 times radius, right? So here's mass 1, here's mass 2, right? Mass 2. And so there's a radius between these two bodies, radius r, right? And we have masses of both objects, and we have this negative sign out here, right? So let's understand this equation. What does this negative sign mean? Right? It means as you increase the radius, right? As you increase the radius, you are actually increasing the gravitational potential energy, right? Why would you say that, right? So you might say, hey, Mr. B, so what's happening here? You're increasing the radius. Because you're increasing the radius, you're actually decreasing the value in front of this negative sign. But then how come the gravitational potential energy is increasing? And then I would say, okay, well, let's look at this. Is negative 1,000 greater than negative 10? And you would say, oh, well, no, it's not. Right? So as you increase the radius and you decrease this number, we are getting closer and closer to negative 1. And negative 1 is always going to be greater than negative 1,000. And because of that, you're going to have more gravitational potential energy as you increase your distance. So if this meteor was right here, right, and the radius was actually this right here, this would have more gravitational potential energy than this one right here. And the closer it was, so if this meteor was right here and it was this far away from the Earth, it would have lower gravitational potential energy. All right? And the way I think about that, so the way I think about gravitational potential energy at long distances is just how I showed you when we were talking about gravitational potential energy on Earth's surface, right? If we have gravitational potential energy, right? So let's go ahead and switch this into colors, right? You have 3 cliffs, right? You have a ball here, you have a ball here, and you got a ball here. The gravitational potential energy is mgh, right? Gravitational potential energy is mgh. Gravitational potential energy is mgh, right? So as you increase, right? As you increase the radius, or as you increase the rate, so let me go ahead and just draw this other equation. Ug is equal to negative g times m1 times m2 over r. So we can see this a little bit better. 2 over r. Okay? And I'm going to go ahead and change colors. All right. So what's happening? We're increasing the height here. Because we're increasing the height, we are increasing UG, right? Gravitational potential energy. Let's just say this is the same mass. Mass 1, same mass 1. Okay? So as this is rolling down, right? These are rolling down. Or actually, let's make this easier. So we're just going to talk about it at the top portion, okay? Okay. As these rocks are on the top, right? These guys are on the top. One second, let me get these colors right. Okay. So as these guys are on the top, they have the same height. They have higher heights. Height 1, right? All of these, the only difference between these three examples is the height. All other variables are the same. So here we have height 2. And here we have height 3, right? So if we write this out, height 1 will be greater than height 2, which will be greater than height 3, right? And because of that, we know that the gravitational potential energy here, UG1, will be greater than UG2 and UG3, right? And because of that, if we compare gravitational potential energy on the Earth's surface, right, or close to Earth's surface, to that of gravitational potential energy from large distances, right, from large distances, what are we essentially doing? We're just increasing the radius, right? Right? If this was the radius from the Earth, right, we're just increasing the radius, and we're increasing gravitational potential energy. So if you're increasing the radius, we are decreasing this value, but we're also increasing gravitational potential energy. So in that sense, if you think about, let's just say you think about a, like this meteor and planet Earth right here, right? Think about this as the same thing as that same meteor being a little bit closer, right? That meteor being a little bit closer. And that way you'll make sense of all of this. All right? All right. So the next thing we're going to talk about is elastic potential energy. Elastic potential energy. Elastic potential energy. Elastic potential energy. And this is also a form of mechanical energy. Okay. Because we're still talking about macro systems, right? So let's just say we have a spring here, and in its relaxed state, right, it is this distance r. Okay, but when it's compressed, when you compress it, let's just say you're compressing it with some object right here, and this coil is coiled up. Usually, this coil is up to here. Right? But because of that, you have a change in displacement of change of x, right? That change of x, right? And that change of x is going to be a factor when we calculate what is known as the elastic potential energy, okay? Because what happens is when we have compressed this coil from here to here, right? We have created or stored energy in the form of this coil, right? Because energy is never destroyed, right? It's either converted into one form or stored altogether. So all the energy is stored within this coil right now, right? So this is called elastic potential energy. And the equation for elastic potential energy is 1/2 a constant K times the change in the displacement squared, okay? And that's how you're going to get the elastic potential energy. Right? And that's just both of these equations, mass times gravity times height, and these are just things that you have to study for your MCAT, right? You have to memorize these. Elastic potential energy, you have to memorize this. You have to memorize gravitational potential energy, right? However, at a large distance, you don't necessarily need to memorize this equation right here, right? You don't necessarily need to memorize this gravitational potential energy equation right here, right? Because this one is very similar to the gravitational force, right? Gravitational force at a distance, right? The only difference is that the denominator is squared, right? G m1 m2 over r squared. Remember that? Remember that when we were talking about forces and Newton's laws? So the only difference here is that this bottom part is not squared, and there's a negative side in front, right? So that is part of those. Those were the only elastic potential energies the potential energies you needed to know for the conservation of mechanical energy, right? So let's also look at. All right. So now the next thing we're going to talk about, right? So we talked about elastic potential energy. We talked about the conservation of mechanical energy at different positions within a system, right? But we never actually defined what a system was, right? So this right here was a system, right? And we excluded frictional forces, and because of that, mechanical energy was conserved at point A, right? It was conserved at point A, point B, and point C. At all aspects, it was saved, right? Because we did not lose any of the energy to frictional forces, right? There was no frictional forces that took away from the system. So now let's talk about what makes up a system and what are the different types of systems, okay? So let's talk about systems. All right. So the MCAT definition of a system is any defined area that we choose to consider separately from the rest of the universe, okay? So any defined area considered separate from the rest of the universe, okay? All right. So now let's look at this. And we're going to also touch upon systems in chemistry when we talk about thermodynamics, right? But we're going to be talking about 3 different systems, okay? We're going to be talking about open systems, closed systems, and adiabatic systems. Right? And usually when we're talking about systems, we try to, because, we're trying to understand what's going around us, so we can't understand everything at once. So we try to create this closed environment, and that's what a system is, right? So now let's examine what a system is and how whoever discovered or labeled these things, systems, open, closed, adiabatic, describe these systems, right? They describe them with 2 variables, okay? And these 2 variables was mass and energy, okay? Mass and energy. Okay, so let's go ahead and look at these three different systems. Okay, so first I'm just going to go ahead and list what happens within with in terms of mass and energy in all the systems. Then I am going to show you an example of each one of these, and then we're going to look at some applications. Okay, all right, so open systems, right, they lose energy. Okay, lose energy, and they also lose mass, or lose matter. It's better to say matter. Okay, lose matter. Okay, closed systems, right, they're going to lose energy, and no matter, but closed systems are not going to lose matter. They're not going to lose matter. Okay, and adiabatic systems don't lose matter, or not lose energy. Okay, so we're not going to lose any energy or any matter in adiabatic systems, but we will lose we will both lose matter and energy in open systems. And in closed systems, we're not going to lose any matter, right, but we will lose some energy. So now let's go ahead and look at what we call an open system. All right, open system. Let's look at an open system. So open system. Okay, open system. So for example of open system, let's go ahead and use this coffee pot. Okay, we're going to use this coffee pot as an example of an open system. And let's just say it's got the little, and let's just say there is hot coffee within this this coffee pot. All right, so an open system, right, by definition, an open system is an environment that can exchange both energy and matter with surroundings, right? With surroundings. So when we talk about the word surroundings, right? When we talk about with surroundings, this coffee pot, right, is the closed system, right? The surroundings would be the air molecules around the system, right? So what an open system is, it's a so if this was closed, right? So let me go ahead and erase this, right? So I meant to say closed, okay? So if this itself is the system, okay? What I meant to say is that this is the system, okay? And this is the surroundings. All right? So if this was a closed system, what we would have to do to make it an open system is to allow it to interact with the surroundings, right? So we have this coffee pot example, right? This coffee pot is hot, and the molecules within it, right, are exposed to the outside world, right? And because it's exposed to the outside world, you see the steam coming off of the coffee, right? That steam is a conversion of is the loss of energy, right, in the form loss of energy, right? Or loss of, well, actually, it's the loss of matter. Let's go ahead and erase that. It's the loss of matter, right? Right? Because what's happening? We have a bunch of H2O molecules here, right? Right? And these guys right here, all right? These guys right here are in the liquid state. And all of a sudden, these H2O molecules are turning into vapor, and they're going into the gas state, right? Because they're going into the gas state, right? What's happening? We are losing matter, right? Because we're losing the content of this system as soon as it goes to the surroundings, because it's reached a temperature where each molecule is able to go from the liquid state to the gas state. So we lose these molecules in that way. So that is how we will lose matter to the surroundings. Now, in terms of energy, right? Energy can be lost. Energy can be lost through heat, right? So we're going to talk about energy and how it's transferred. Energy is usually transferred in two ways, okay? Energy is either transferred through frictional forces, right? Which is the same as heat, right? Heat or frictional forces, right? Or energy can be transferred in the form of work, okay? Work. So we are losing energy to the environment because the molecules on this coffee pot are interacting with the molecules inside this coffee pot. So like the hot water and the caffeine molecules or whatever, they're interacting with the side and they're colliding with the walls of this these other molecules, and they're losing the energy, kind of like a billiards ball, right? You aim to use the white ball to hit another ball, but that ball will actually the ball that you hit actually gains the momentum, or it gains the kinetic energy, while the other one loses it, right? That white ball usually stays in place or loses energy when it gets hit, right? Just like that, when these molecules come and hit the side of the surface, the energy is transferred to those outside molecules, and because of that, those molecules they bounce off heat, and we sense the heat on our hands. That is the transfer of energy, right? So we're losing energy to the environment. So that is why we call it an open system, right? Because we're losing matter and we're also losing energy. So now let's look at a closed system. Okay, so how do we define a closed system? Closed system. All right, so what is a closed system, right? So a closed system, right? A closed system can exchange energies, can exchange energy as heat or work, right? As heat or work, but not matter. But not matter. All right? It cannot exchange matter with surroundings. With surroundings. Okay? So let's think of a closed system, right? So a closed system. Okay, so let's just think about a stew. Okay, we're making a stew. All right? So let's say we're making this stew, and we have this stew, and we're making this stew, right? And this stew or actually, let's just say this is like a pressure cooker, okay? So, or like a pressure cooker, okay? So let's just say this is a pressure cooker, right? And so the top is closed to the environment as well, okay? The top is closed to the environment as well. All right? Pressure cooker. We're drawing the pressure cooker. All right? So in this situation, and we have a stove, okay? We have a stove on the bottom, right? And the stove is giving heat into our closed system, okay? Our closed system is gaining heat, okay? Our closed system is gaining heat, okay? And what did we say about closed systems? We said closed systems, they do not lose matter, but they lose energy. So no matter loss. Matter is not lost, okay? The contents within this pressure cooker are not lost to the environment, okay? One thing. Now energy. Energy can be lost. Energy can be lost, okay? No matter loss, okay? Matter is not lost, but energy can be lost, okay? So let's think about this system, right? How can and what did we say about energy, right? We said energy has two outlets, right? Once the energy is taken within and absorbed by the molecules or transferred from one source of energy to another, right? So here would be thermal energy, right, into chemical energy, right? Because now the molecules have energy, right? So now it's one form of energy transfer to the next. How can energy be lost, right? Energy can be lost, like we studied before, by either those molecules doing work like they were doing before, right? But we're not going to measure that work, okay? Because that's you're going to have to add up all the work done by all the molecules, right? So energy can be lost by work, or work done by the molecules, or it can be done by the transfer of heat, right? So the transfer of heat. So let's see how that will take place, right? So matter is not lost because the environment is closed, and because of that, none of the matter within this crock pot or this pressure cooker will leave, all right? Okay, so now what about the energy? The energy can be lost, right? Like we saw in our example here, right? When we talked about this car engine, right? This was an example of a closed system, right? Because there was gas coming into the car, right? Or gas molecules coming into the car, and the system was closed off, right? This there's no opening here, okay? So this part is actually closed off, okay? And because of that, these molecules had to expel the energy somehow, right? And what are the two ways that energy can be expelled? Either by doing work, right, or by releasing heat into releasing heat, right? So that's why we describe that some of the energy, right, is going to be gone in the form of, right, is going to be gone in the form of heat, but also there's going to be work done by the system on this piston, right? These molecules are going to expand, and it's going to push this piston down, right? And because it's pushing this piston down, it's going to cause these tires to this axle, and eventually these tires to rotate, right? and that was the application of torque that we were talking about, right? So let's go. So, and this is an example of a closed system, right? So we already discussed the closed system, right? So now let's go back. And look at the closed system. Okay? So let's look at the closed system, okay? So energy can be lost, right? Energy can be lost by doing work. In this case, there's no outlet for the work, right? Now, in terms of heat, we can lose heat, right? Heat is the same thing as frictional forces for the MCAT. Frictional forces, okay? And remember how we described frictional forces when we were talking about we were talking about translational motion and frictional forces of the tires of the car, and how there was a normal force, right? And how the frictional force was based off of a coefficient of friction times the normal force, right? And we talked about the creation of frictional forces through the interaction between the molecules of the tire and the road itself, right? Because they had two different molecules, and the outer shells were interacting between the molecules, right? That is frictional forces, right? And as soon as you start the car and you start driving off, those frictional forces are going to give off heat. So there's going to be a slight change in the temperature there, right? And that is why we refer to heat as frictional forces, all right? So if we come back here and we look at frictional forces, right? And we refer to frictional forces as similar to heat, and we go ahead and put our hand here, right? Let's just say this is our hand. We put our hand here. We're going to absorb some heat, right? And that will be an example of frictional forces that occurred because of the matter that was within the system interacting with the outer molecules of this pot, okay? And that's going to cause a frictional force, right? Maybe not the right term, frictional force, but it's going to cause heat. And we're going to sense that in our palm of our hands, heat, okay? So in that sense, energy can be lost, right? But no matter is lost in a closed system, because a closed system is closed. It's closed to the surrounding, right? So now let's talk about an adiabatic system. Okay, so let's go back here. So let's talk about adiabatic system. Adiabatic system. All right. So let's talk about the adiabatic system. In an adiabatic system, you do not lose heat, or you don't lose energy or matter, okay? Not lose energy or matter. All right. So let's talk about the adiabatic system, right? So in an adiabatic system, right, we have these molecules, right, within our system. And the idea within an adiabatic system is that no energy is lost, right? So no energy is lost from the movement of these molecules onto the walls of our system, right? Matter does not move from one side of the system to the surroundings, right? It doesn't move from one side of the system to the surroundings. So this molecule here will not move out here. And usually, if we look at car engines, okay, so if we looked at the car engine, okay, So if we looked at the car engine, okay, what we want is we want an adiabatic system, right? Because we want to be able to not lose any of the energy. Not lose any of the energy within the system. Right? So when we say we don't want to lose any of the energy in the system, right? What we're saying is that we don't want to lose any of the energy in the form of frictional forces, right? Frictional forces as in heat, right? Or we don't we don't want to lose any of the forces in terms of frictional in terms of heat, right? So so that, right? We would like to have an adiabatic system, right? But we will lose. So in a car engine, we are going to lose. We're going to lose energy because they are going to be transferred in the form of work, right? But what I was trying to say is that we have this adiabatic system, right? But what we want is we want to maximize the amount of work done by the system when we are talking about the pushing of the pistons, right, to create that force, right, so we can increase the torque. So in essence, we want an adiabatic system in the sense that we want our closed environment to not be able to take up any of this heat, right? We don't want our system to be able to take up any of this heat, so that we can use that energy, right? We can use that energy from these molecules, right? Because these molecules, when the energy is put into the system, they're going to what? They're going to expand, right? They're going to expand. They're going to expand. They're going to expand. So there's going to be this downward force. And to maximize this downward force, we would want to reduce the amount of heat transfer to the surroundings. So in a sense, our car engine is kind of like the car engine example can kind of be considered an adiabatic system, but is not considered an adiabatic system because it doesn't meet the requirements. But it is similar to one in the sense that we don't want the heat to be lost to the surroundings, and because we want to use all the stored energy that we put in to this car system so that we can use that to create force, to create our torque, to move our cars, right? So that is why I was referring to the car engine, and how engineers, they want to optimize the efficiency of the car engine. So they want to make sure that the amount of work that is done is transferred wholly to the function of the car as opposed to the outside environment. So that's why I was trying to refer it to as an adiabatic system. All right. So the next thing I want to talk about, okay, is an application. All right. And this application is going to be about, let's see, application is going to be about adiabatic system, the adiabatic system and its reference, adiabatic system, and how we look at the universe, right? So actually the universe is considered an adiabatic system, right? So when we think about the universe, so the universe is an adiabatic system, right? And that's where we get this idea of the conservation of energy, right? So when we talk about the conservation of energy, So the conservation of energy says that energy is neither created or destroyed, right? Neither created or destroyed, right? Because all the energy within the universe remains within the universe, right? It's a system, right? Energy is not created, it's not lost, right? Just like matter is not lost, right? So when we talk about the conservation of energy, just think about, okay, well, the universe is a adiabatic system, and because of that, the conservation of energy makes sense, and it's a little bit easier to think about the conservation of mechanical energy, right? And understand that the mechanical energy, right, when we're looking at this this hill, right, we're looking at this hill and we're looking at position 1, and we have only potential energy, right, potential energy full, and we're looking here and we have potential energy and kinetic energy, and then we're looking at here and we only have kinetic energy. It's understandable why we don't lose any energy, right? Because our universe is an adiabatic system, and because of that, we will never lose any energy. So at each point, we will maintain the total mechanical energy, right? So that's another idea that kind of helps me remember the idea of the conservation of mechanical energy. Okay, so total mechanical energy, right? They'll be the same at all points, because energy will never be lost, right? Because we are living, or we define the universe as an adiabatic system. All right. So now that we've described the conservation of mechanical energy, conservation of energy, talked about closed system, open system, adiabatic systems, and the application of a car engine with these systems, and the different types of energy, how they're transferred. Let's talk about what work is, right? We're going to define what work is. We're going to learn about what work is, okay? Let's learn about work, okay? And later we're also going to be talking about power, okay? Work and power. So work, as described before, is force times distance times cosine of theta, right? The force times the displacement times the cosine of theta, right? So in other words, in order to calculate work, right, you need a force in one direction, and you need the displacement also in the same direction, right? Because in order for us to calculate work, force and displacement has to be in the same direction, so that cosine of 0 would be 1, right? So that way work will just be force times distance. And in most cases, this will be how they're going to give it to you. Work is also defined as the change in energy, change in kinetic energy, right? Between two different from the initial starting point, initial state, let's just say, of molecules, and the final state of molecules, right? So you can have, so in order to calculate work those molecules done in our previous system, we would have to know the sum of all the kinetic energies of each individual molecule, right? So Ke final minus Ke initial, right? And that will be another way of calculating work. So what are the units for work then? work is newtons, right? Force is in newtons, and distance is measured in meters. So is Newton meters, right? Be Newton meters. Newton meters, right? So if work is defined as Newton meters here, then work here will also be defined as Newton meters here, right? What did we say Newton meters was equal to in our previous lecture or previous slide? Let's check it out. When we described energy, we said that Newton meters was equal to joules. So energy and work have the same units. Isn't that interesting? So Newton meters or joules. All right. All right. And also the only difference between work and power is the rate. Power is the rate at which work is done, right? The rate at which work is done. So if we look at this, power is the rate at which work is done over a period of time, right? Anytime we talk about rates, we're talking about in terms of time, like cycles, right? So power is work done over time. We can also measure power as the final kinetic energy within a system minus the initial kinetic energy in the system, the time that it took for that system to gain that amount of kinetic energy, right? And we will get what is known as power. Okay? Now power, right, can be, so let's look at the unit of power, right? Unit of power can be joules over seconds, right? Because kinetic, it's energy over time. Or it can be Newton meters over seconds, right? Or we can break it down even more, right? We can break down newtons. Let's go ahead and break down newtons a little bit more. What do we know newtons is equal to? We know newtons is equal to kilograms meters per second squared, right? And if we multiply that by meters per second, right, we can also find out that that the Newton meters per second is, and we can also break it down like this, right? If we had let's just say we had breaking down this equation, right? Because the MCAT's going to ask us to look at each of these equations from all angles, okay? So now let's go ahead and look at this. Look at this this power equation that we came up with, okay? So power is equal to work over time, which is equal to KEF minus KE initial over time, right? Which is equal to the same thing, right? How did we define? Well, what is the formula for kinetic energy? Kinetic energy is equal to 1/2 mv squared, right? So let's go ahead and break this down. So we have 1/2 mv final squared minus 1/2 mv initial squared over the time that it takes, right? So the time is going to be broken down into seconds. But let's go ahead and just use time right now, right? So that's power. So now let's go ahead and take out 1/2 m from the equation, okay? So let's just say we took 1/2 m out of the equation, and what we were left with, right? What we were left with was, or actually, let's actually do something else. I want to show you a little bit more useful breakdown of the power equation, okay? Because you might go from kinematics and then they want to know the power You might go from kinematics to they might give you kinematic tools within the question, and they would probably want you to calculate power. All right, so you need to know how to break down this equation so you can use the kinematic variables that they give you. Okay, so work, right? We talked about it being force times distance times cosine theta, right? And it said it's over time, right? So let's break it down. Do you see any way we can break this down just a little bit more? All right, so let's go ahead and break this down. Right? Distance divided by time is what? Distance divided by time is velocity, right? So force times velocity times cosine theta is also equal to power. So you can also use this equation to find the power of the system. All right. And so the final thing that I want to do is go ahead and I'm going to go ahead and do some practice problems with you. All right. So let's go ahead and look at the practice problem here. Right. This practice problem. So let's just say we have a meteor. So we have a meteor with mass 1 kg, and it's moving at 10 kilometers per second, okay? And it collides with Mars atmosphere, okay? So let's just say it's Mars atmosphere. All right? So this meteor penetrates 100 kilometers into the atmosphere. And disintegrates. All right? What is the average force, right? What is the average force? What is the average force on the meteor when it enters the Mars's atmosphere? And that's the question. Okay, so let's change colors here. Let's try purple, okay? So what is the average force? So we're looking for force, meteor with a mass 1 kg moving at, so let's just draw this picture real quick. So we have a meteor right here, right? It has a mass of 1 kilogram, right? This mass is moving at okay, so let's just say it's moving at a velocity, right? Velocity of 10 kilometers per second, right? And it collides with Mars's atmosphere, right? This meteor penetrates 100 kilometers into the atmosphere and disintegrates, okay? So now it's traveling, right? So this meteor is going into the atmosphere, so right? And let's just say that this is Mars, right? So let's just go see. Mars 1. Right, let's just say those are the craters of Mars. Let's just draw Mars. Okay, so this is Mars, right? And Mars, and now we are 100 kilometers, right? 100 kilometers away, right? We're 100 kilometers away from the atmosphere. All right. So first thing we have to do is we have to convert everything, right? First step, convert everything. We usually for the MCAT we all the answers will be in meters per second, meters, kilograms, newtons, joules, right? So let's first go ahead and convert this velocity into meters per second. All right. So that's the first thing that we're going to do. Okay. So let's do our dimensional analysis, right? 10 kilometers per second, right? Right. We have 1 kilometer, right, which is equal to how many meters? 1,000, right? So now we know that the actual velocity is what? 10,000 meters per second, right? So it's 10,000 meters per second. Right, and now let's look at this distance, right? We need to convert the distance as well back to meters, right? So let's go over here and do our dimensional analysis again. All right, so let's go over here, 100 kilometers. And we're going to say 1 kilometer is equal to 1,000 meters, right? Cancel, cancel. And we realize that this is now 100,000 meters, right? That is the distance. That is the distance between the crater and Mars, right? So now let's go ahead and draw this, right? So let's go ahead and draw this. We're going to redraw this with our new measurements, okay? So let's go over here. We have our crater, right? Our crater is how long? One kilogram. 1 kilogram, right? 1 kilogram at 10,000 meters per second. 10,000 meters per second, right? That kilogram is traveling over a period of 100,000 meters, right? This guy is going from here to Mars. So let's just say this is Mars over a period of 10,000 meters, right? 10,000 meters or 100,000 meters, sorry. 100,000 meters. So raise this. 100,000 meters. And what is the question asking? It is what is the average force on the meteor which is entering the Mars atmosphere, right? All right. So let's go ahead and solve this, right? So the first thing that comes to my mind is like, okay, well, maybe this molecule is this meteor is traveling, right? So it has some type of kinetic energy, right? It's a mass, it's moving with the constant velocity, so we have a kinetic energy, right? Okay, so if it has some type of kinetic energy, right? Then it probably started off less and then it accelerated, right? So then I'm also thinking that there might be force involved, right? So first thing I'll do is go back to our equation, right? Work is equal to FD cosine theta, right? Now write it all out, right? We also know that KE final minus KE initial is equal to work. And we'll go ahead and solve this equation, right? Work is equal to 1/2 mv final squared minus 1/2 mv initial squared, right? So initially, the velocity was 0, right? So we're going to cancel out this term. So our work for our system is equal to this 1 kg system times the velocity now, which is 10,000 meters per second, right? Squared, right? So now let's go ahead and calculate our work. All right, so the way I would calculate this is I would go ahead and convert this 10,000 meters per second into exponential form, right? So let's make that happen. 1, 2, 3, 4, right? 4. So 1 times 10 to the 4th meters per second. Square it. 1 kg. Add 1/2, right? So our work. So let's erase this. So our work done on the system is actually, let's see. Remember, whenever we're doing exponents, we have to add them, right? 10 to the 4th plus 10 to the 4th is 10 to the 8th, right? 10 to the 8th. 10 to the 8 meters per second, right? 1 times 10 to the 8 meters per second times 1/2, right? So now we have a work that's equal to 0.5 times 10 to the 8 meters per second, right? So if we move our decimal place back one, right, we're going to get 5 times 10 to the 7, or 10 to what? So if we go left, if we go left, we add, right? And if we go right, we subtract. So are we moving left or are we moving right? We're moving right, right? So we subtract. So 10 to the 7 meters per second. All right? Okay. So now let's look at what the question was asking. It's asking for the average force, right? We have our equation here. Work is equal to force times distance times cosine of theta. So all we do is we're going to come back over here and we're going to plug and chug. 5 times 10 to the 7 meters per second, right, is equals to the force, right, because the force is also going to be here. And we're also going to be looking at the distance traveled, right? So the times the distance traveled times the cosine of theta. Cosine of theta is 0 because the force and the direction of travel is the same, right? Force is going downwards. The direction of travel is also the same, right? So since both vectors are going in the same direction, the cosine of theta is going to be 0, right? Which is going to be 1 times distance times force, right? So now 5 times 10 to the 7 meters per second. Now all you have to do is divide that by our distance. So we have 1, 2, 3, 4, 5, right? So 1 times 10 to the 5. Okay, that's our distance, right? We just converted it back into meters. 1, 2, 3, 4, 5, right? That's about right. So we're going to do 5 times 10 to the 7 meters per second. And we're going to divide that by 1 times 10 to the 5 meters per second. And we're going to get the net force, all right? The net force that's experienced as this meteor enters the atmosphere, right? And that answer is going to be 5 times 7 minus 5, 2 meters per second, right? And that is going to be the answer to this question right here. All right. So another thing that I wanted to point out to you was that you could actually use the gravitational potential energy to possibly solve this equation, right? If they had given you the mass of the Earth, you could find the potential energy, right, of the system from this far distance, and you could also found the potential energy of the system, of the system if it was close by, right? And the difference you could use to determine the force, right? Because the work, you could use that, right? So you have to really think in multiple different ways when you're approaching questions, right? So actually, that you cannot use but you cannot use the gravitational potential energy to solve that equation, right? But that is something you should think about, right? So these two objects has a gravitational potential energy, right? And that is something that is good that you pointed out, that was pointed out, but it wasn't necessarily true, right? You can't use it for this example, but that's actually good that you need to be thinking in that way. All right, so yes, all right. So that sums up this episode. I hope you guys liked it. If you liked it, please give a thumbs up. Um, but I hope as soon as I finish all of these series on physics, chemistry, OChem, biology, biochemistry, that I can also include a question session where I'll be only doing questions for a straight 2-3 hours on a bunch of different topics in physics, biology, biochemistry, just to help you guys nail down some of the conceptual stuff. But this is the end of this lecture, and then our next lecture will focus on ideas in momentum, machines, and radioactive decay. All right, thanks. Please give me a thumbs up. Thanks.